Hello, this is Kara Tierney from Monroe Community College, and in today's video we're going to talk about Hess's Law, which is one method of calculating enthalpy or heat of a reaction. The derivation of Hess's Law comes from the fact that the enthalpy change of an overall process is the sum of the enthalpy change of every individual step. This is because enthalpy is what's known as a state function. To explain what a state function is, I've taken a picture of two ways you can climb a mountain. So I have path A, which is a direct route up. This is not going to be a fun way to climb a mountain, but it is the shortest way. Or path B, where you have the switchbacks. So it's not as steep, but you have to walk a lot farther. So when we're looking at these two paths, path A is shorter. Path B is longer, and so the distance traveled is what's known as a path function. So when we're looking at how far each person walked, it's different. So it's determinate by which path you take. If we look at the altitude gained, or how much height you've climbed, that's a state function, which is the same as enthalpy. Enthalpy is a state function. It doesn't matter how you get there. The overall difference is what matters. And so when we take a look at path A and path B, both gain the same amount of altitude in different ways. Just one is much more gradual than the other. This is called a state function. Doesn't matter which way you go, you both accomplish the same altitude gain. So enthalpy is a state function, so it doesn't matter if you do a reaction in 1 step or 5 steps. If you're talking about the same reactants and the same products, then you're going to have the same enthalpy change. And so what we can do is we can use steps to get to an overall product. And this is used quite a bit in organic chemistry or industrial chemistry, where we use several different steps to get to an overall product. And so what I'm going to do is I'm going to maybe overload you and tell you all the steps of how to use Hess's Law, and then we'll do an example so you can see how this step method is used. So how you calculate your enthalpy of a reaction using Hess's Law. First of all, how do you know if you have a Hess's Law problem? It's actually quite obvious. If you are given multiple reaction equations, this is a Hess's Law problem. You're going to be adding up equations over the process of your problem. So the first thing that you do is you need to write the reaction for which you are determining your enthalpy of reaction. Now, sometimes this reaction will be given to you, and sometimes it will be described for you. So the two ways in which it could be described is if you're asked for enthalpy of formation, you may have to write the formation equation for that substance, or you may be asked for the enthalpy of combustion, and so you would have to write the reaction equation where that substance undergoes combustion with oxygen. You may also just be given the reaction equation that you need to calculate enthalpy of, and that's the easiest case because you can skip right over number 1 and start with number 2. And what you're going to do is you're going to be given several reactions, at least 2, and you're just going to take one at a time. So start with your first reaction equation given. And I want you to look for a substance in that reaction that is also in your final equation. And I want you to ask yourself a couple questions. Is that substance on the correct side of the equation? Does it have the correct coefficient? That's what you're looking for. And if you have to manipulate the equation so that you can answer yes to either of those questions, whatever you do to the equation, you need to do to your delta H. And I'm going to go over this as we do an example. And then you're going to rewrite your reaction equations so that you could say yes to both A and B for substances in all of your equations that you're looking at. And you're going to check to make sure that those new equations add up to give you your final correct reaction equation. And then you're just going to add up all the delta H values for those corrected steps. So let's do a problem because this may seem a little intimidating. So let's just look at the problem we have here, which is example problem 3. You are asked to calculate the standard enthalpy of formation of CS2 liquid given the following information. So you're given 3 reaction equations. Right away, you know this is a Hess's Law problem because of that. And you're asked to calculate the standard enthalpy of formation. That means you have to write the reaction equation for the standard formation of that compound, CS2 liquid. And then what we're going to do is we're going to compare that reaction to the 3 reactions that are given to us. So let's start off with step number 1, which is writing the reaction for which we are asked to determine delta H reaction. So right now, I want you to practice writing your standard formation equation for CS2. Take a moment and do that now. Okay, so this is how we write the reaction equation. If you recall, we know that CS2 is going to be our only product, and it's going to be formed from its 2 elements, C and S. Then we balance the equation so that our final product has a coefficient of 1. So now what we're going to do, now that step number 1's taken care of, we're going to write the reaction. Now the next thing we do is we start with the first reaction given, and we look for a substance in this reaction that is also in the final reaction equation. So we're just going to number our 3 reactions, 1, 2, and 3. All right, let's look at our first reaction. There are 3 substances in this reaction. We need to find one that is also in our final reaction that we want, okay, and that's this one with the star. That's what we want. And hopefully this substance isn't going to be in the other reaction equations, because that can make things a little messy. So if you notice, solid C is in both of our reaction equations. So we're going to compare those 2. And we're going to ask ourselves 2 questions. First, is it on the correct side of the equation? Yes, it is. So we don't need to flip the equation. Second question we ask, does it have the correct coefficient? Well, we know that it needs to be in our final reaction equation on the reactant side with a coefficient of 1, so we're okay. So what we're going to do is we're going to rewrite that reaction as is, because we didn't have to make any changes. Oh, I see here I have a remnant of how the reaction was previously written, so you can just ignore that right there. So now we're just going to do step 2 and 3 for reaction 2. So reaction 2, let's do the same thing. Let's look for a substance that is in both this reaction 2 and our final reaction, and that's going to be our sulfur. So our first question we ask, is it on the correct side of the equation? Yes, it's a reactant and we need it to be a reactant. Second question, is the coefficient correct? No, we need a coefficient of 2. So what we're going to do is we're going to multiply this entire reaction by 2. We're going to multiply all of these coefficients and our delta H. Let me just make a note. Our first reaction we kept as is. We're going to rewrite the second equation, multiplying all of the coefficients by 2, including the delta H. Let's look at our third equation. Let's pick a substance that is also in our final reaction. And that's going to be our CS2. So now let's ask ourselves the 2 questions. First, is it on the correct side of the equation? No, we see that in equation 3, it's a reactant. In the final equation, it's a product. So we need to flip this equation. Let's make a note of that. And our next question is, does it have the correct coefficient? Yes, it does. So we're just going to flip this equation, which means all of the reactants become products, all the products become reactants, and we're going to change the sign of our delta H. So we're going to rewrite that, and you'll notice the sign of delta H changed. What we need to do now is step 5, we need to check to make sure the new equations add up to give us this final equation. So I'm going to show you how to do that. We're going to look, when we add this up, if you have a substance in 2 equations on the same side of the arrow, they're going to be additive. So these oxygens here, those are going to add with each other to become 3O2. When you have the same substance on opposite sides of the arrow in 2 different reactions, they're going to actually cancel out. So this 2SO2 is going to totally cancel out. You can have partial cancellation, so say this was just a one SO2, then just one of these other SO2s would cancel out. But because they're both 2s, they totally cancel out. Take a look. Do you see anything else that cancels out? The CO2 cancels out with the CO2. And finally, these 3 oxygens that added up with each other actually cancel out with the 3 oxygens in the third equation. So these all cancel out. So we write what's left over. We have our carbon, our 2 sulfur, and that's it for the left side of the equation. And all we have left on the right side is CS2 liquid. Now compare that to what we wanted up top. Guess what? The same. That means we did the right thing. We calculated that correctly. Now what we're going to do is add up all of our delta H's, and that is going to give us our overall enthalpy of reaction, which is positive 86 kilojoules. So now I would like you to give a shot for the your turn problem. You're given 2 reactions, and you're asked to calculate the delta H for the final reaction, which is right here. So this is your goal. You want these 2, you want to manipulate them so that they can add up to give you this last equation. I want you to follow the steps of Hess's Law and see if you can get a final delta H. We'll go over this question in class, and I can take any of your questions at that time. And I'll see you there.